The Earth's climate has gone through periods of being wildly different to how it is today. We've seen how it can change at scale. We've seen changes that led to the flourishing of life, and we've seen changes that led to the devastation of life. So let's take a quick tour through approaching 5 billion years of history, and at the end we'll reflect on any lessons that might present themselves. Important caveat before we begin: the further back in time you go, the less concrete the evidence is, as you'd expect. While we have a pretty good idea about the broad brush of what happened, many of the details will never be known to us, and some of what we think we know is disagreed over and argued about. Personally, I think it's a miracle that we've been able to work out as much as we have. The part that we know the least about, unsurprisingly, is going back a full 4.5 billion years ago, when the planet was recently formed and was one big seething ball of molten rock. The planets were just forming, the sun was significantly weaker than it is today, about 70% of its current strength. That's because as hydrogen is gradually converted to helium in the sun's core, then that core grows denser and hotter over time. We estimate that the average global temperature at that point was around something like 420 degrees Celsius. Toasty, in other words. From what we can tell, the atmosphere was made up mostly of methane and ammonia and other gases that would be pretty toxic to any life today. Meteorites and asteroids were frequently slamming into the surface of the planet. It was one big party. By the time of 4.2 billion years ago, the Earth was beginning to cool and become more stable. The atmosphere had become highly rich in nitrogen and carbon dioxide. Heavier materials like iron sank to the bottom. Lighter materials like silicon rose to the top. This created the Earth's layered core and mantle, which was going to turn out to be essential for any chance of us appearing, because around the 4 billion years mark, Earth's magnetic field formed. Without the magnetic field, which was around 10 to 50% of its current strength, the Earth would have been blasted by harmful rays by the sun, probably would have lost any atmosphere it had as a result. By about 3.7 billion years ago, the temperature of the planet had cooled, although still pretty hot compared to today, an average global temperature of something like 40 degrees Celsius. Liquid water had formed oceans, the Earth's crust was already being moved around by tectonic forces. And at this point, there's the first evidence of biology. As you can imagine, trying to trace the appearance of single-celled organisms nearly 4 billion years ago, kind of tricky. Nevertheless, it's around this time that life appeared, just because we know that 1,000 million years later, we know that the organism that was held to be the last universal common ancestor, the granddaddy of every single living creature, plant or animal on Earth today, was in existence. Wasn't the first life form on Earth, but all its contemporaries died out. Note that the atmosphere was still nearly all nitrogen. There was zero oxygen. So for the time being, any and all life was anaerobic, and it stayed that way for quite a long time. Creating energy without oxygen's not easy, which may be why the earliest life took so long to evolve, and why, after a while, there was an important innovation. Sometime after 3.2 billion years ago, the first photosynthetic organisms appeared, Cyanobacteria. In other words, they were taking sunlight, using it to convert into energy, a process which produces oxygen as a byproduct. How many oxygen-producing bacteria do you need to actually make a measurable impact in the atmosphere? Well, a heck of a lot. And it takes quite a long time to get there, because there were some natural oxygen sinks, such as iron, that would react with the oxygen to rust before that oxygen could start to accumulate. And before we got to that point, we had some business to deal with, like hitting the first ice age, the Pongola Glaciation. It's not thought to have been a worldwide glaciation, but it's a reflection of the fact that with CO2 weathering out of the atmosphere and the sun being significantly weaker than today, temperatures could fall to the cool side. Still, on the warm side, relatively speaking, probably because of the more potent greenhouse gas methane, which was a significant component of the atmosphere. That glaciation ended after about 120 million years. It's the sort of statement that just trips off the tongue while talking about what was seen as a relatively minor glaciation. 120 million years still seems like a huge length of time to me. 2.6 billion years ago, well recovered from the earlier glaciation, the presence of cyanobacteria really began to make itself felt and oxygen production started shooting up. The makeup of the atmosphere was mostly nitrogen, steadily growing level of that oxygen, plenty of methane and CO2. But the oxygen level in the atmosphere, as it went up, turned out to be toxic to a lot of those early anaerobic organisms. And that led to the first mass extinction, what's known as the Oxygen Catastrophe. And here's a lesson in relative biology. Without oxygen, we wouldn't be here. So, a catastrophe for anaerobic bacteria, pretty good for us. However, we weren't going to come along for a long time, and it's probably just as well. Because although on the one hand, life forms were using oxygen to increase their metabolism and to produce energy in significantly more effective ways, there were a few less good consequences as well. Specifically, the appearance of oxygen in the atmosphere led to the breakdown of the methane, which had been up till then the most effective greenhouse gas. Now, you probably know that we say that methane breaks down relatively quickly in the atmosphere, and that's why, because of the oxygen. But here, its disappearance, along with the fact of that weaker sun and CO2 being relatively low, that led to the first really big glaciation, the Huronian glaciation. Studies have suggested that the dramatic drop in methane would have caused a surface temperature decrease of around 20 degrees C. This was 2.4 billion years ago, and the Earth completely froze over, becoming snowball Earth. Once the world is covered in ice, the white reflective surface also more effectively reflects back the sun's rays, so reinforcing that cooling effect even more. Unsurprisingly, that was something of a major extinction event, and for the duration, photosynthesis stopped, meaning that oxygen levels slowly started to decline. Once the planet had entered a snowball phase, how would you ever get out of it? Well, likely because of the buildup of carbon dioxide. Now, CO2 is normally weathered out of the atmosphere by contact with siliceous rock. But that can't happen in a snowball Earth because it's all under ice. So over the millions of years, snowball Earth persisted. Volcanic activity pushed out more and more CO2 into the atmosphere where it would accumulate until it reached a level that it was sufficiently strong to begin the melt. 1.5 billion years ago, a photosynthesizing cyanobacteria became integrated with another cellular life form, a eukaryote. It became an organelle within it, which was the very first step towards more complex life forms. That eukaryote became the ancestor to all plants and algae. Another 100 million years later, and note again, that's a really long time, but it just zipped past in an instant. The earliest algae appeared. Another 100,000 years, so 1.3 billion years ago, the first fungi spread onto the land. It's been nearly 2 billion years since the first simple life forms came into existence, and we've managed algae and fungi, simple forms. Slow evolution, largely because of the hostility of the environment to life for much of that time. But from about 1.2 billion years ago, life starts to become ever more complex. It may have been helped by the formation of the planet's inner core, which strengthened the magnetic field and gave us more cover from the effects of the sun. That helped the earliest photosynthetic life to move onto the land, and it led to the formation of sex. Not entirely recognisable in the modern context, but the enormously advantageous process of creating genetic diversity nonetheless. 840 million years ago, land plants and algae diverged evolutionarily, and by this time we've been waiting for a glaciation for ages, so naturally two came along at once. The Sturtian glaciation around 716 million years ago saw temperatures drop to about minus 30 degrees C and another snowball Earth. That lasted for about 60 million years. Again, a really long time, except not. Then it ended, and for a glorious 7 million years or so it was rather toasty, and then we were down to minus 40 degrees C for the Marinoan glaciation, which lasted for about another 19 million years. It's really miraculous in my mind that life was able to survive at all through that sort of process. But even if the Earth was completely frozen, and we don't know for sure how much it was entirely, life could have survived near hydrothermal vents in meltwater ponds near to volcanoes. What caused these glaciations? As with much of its distant history, we don't really know for sure. However, we do know that there was massive ongoing volcanic activity associated with the breakup of a Rodinia supercontinent. The correlation of that event with dramatic change in climate led scientists to try to work out how those two could be connected. At first, it was proposed that a large outpouring of magma rock would have resulted in increased weathering of CO2 from the atmosphere, sufficient to trigger the process of cooling, which then becomes self-reinforcing after a certain point. But a paper in 2017 by MacDonald and Wordsworth argued that the decline would have been a lot slower if it had been that sort of weathering process. They suggested instead that the location of the volcanoes and the relatively less hot climate at the time meant that significant quantities of sulfur were injected into the stratosphere, blocking out the sun and causing a major cooling. Now, we've seen cooling periods when individual volcanoes have managed to throw up lots of sulfur into the atmosphere, but those have been short-lived one-off events. In this case, it was sustained, and it was massive. I mean, these volcanoes spanned almost 2,000 miles across Canada and Greenland. And at some point, the cooling reached a critical point, and the albedo from encroaching ice makes it a self-reinforcing process. Once the ice reached the latitude of present-day California, the positive feedback makes the snowball effect unstoppable. In periods where the Earth's environment is already cooler, the stratosphere is lower, and so it's more likely that eruptions would manage to reach that stable layer and then spread throughout the atmosphere. So these could have created the snowball Earth outcome because the location was exactly the right place to inject sulfur for the most efficient dispersal worldwide. Once those glaciations passed, we do know that the oxygen-producing organisms exploded, and between 632 million years ago and 580 million years ago, the atmosphere went from about 3% to 15%. And as oxygen enriched the atmosphere, one of the results was that the ozone layer thickened. Before there was an effective ozone layer, life was pretty much restricted to shallow water, because the water was needed to shield the harmful radiation. The thickening of the ozone layer allowed life to diversify on land, and it was just about ready to do so. One more short-lived glaciation came along, the Glacia's glaciation, just a mere few 100,000 years long. Just gave you long enough to get your hair done, really. Once that went, we saw what's been described as the Avalon Explosion. This was a period of diversifying life that produced the first complex multicellular organisms. This is an illustration of what that might have looked like based on the fossils that we've been able to track back to that time. Indeed, there seems to have been something about global catastrophic events that encourages the next generation to more creatively diversify to fill the newly emptied niches. So along came one more glaciation, the Baker-Neurion glaciation, 546 million years ago, and that led to what's been called the Cambrian explosion. The diversity of life surged to unprecedented levels. Hard-shelled invertebrates appeared in the oceans, along with many of the major phyla that make up modern animal life, along with some that didn't make it this far. The first reefs appeared, all sorts. It was a real party. Oxygen levels were high at this point, higher than they are today, which probably enabled the boost in diversity. CO2 was also higher, and that meant that average temperatures would have been somewhere between 22 degrees C and 28 degrees C. Then, around 513 million years ago, there was a mass extinction event that saw off a large portion of marine life, estimated between 50 to 80%. What happened? There's evidence suggesting that widespread volcanic eruptions around the Kalkarinji Large Igneous Province, which could have injected large quantities of greenhouse gases into the atmosphere, leading to higher temperatures, ocean acidification, and a loss of ocean oxygen. Over the coming hundreds of millions of years, we saw a another explosion of life, the Great Ordovician biodiversification, which saw a diversity of creatures taking the place of the Cambrian life forms that had been wiped out. 466 million years ago, plants colonized the land. 415 million years ago was the age of fish and the very earliest forerunners of sharks. We breeze through these dates, by the way, but just pause to notice every now and then that was 50 million years later, and I still hold that's a really long time. 392 million years ago, the first insects are recorded, although they probably predated that fossilised evidence. 376 million years ago, the evolution of leaves. And then another mass extinction. And this one wiped out half of all marine life, again, triggered by volcanic activity, the Viloi traps in Siberia. 314 million years ago, we saw the formation of Pangaea, the single supercontinent that eventually broke up to become the map that we know today. And with that came the uplift of dry land. Many of the newly exposed areas from the sea became vast swamp forests. Club mosses that are basically ground cover today grew to enormous heights then, as high as 100 feet. This was the start of the age of amphibians, which were the first vertebrates to make the move to land. We also saw the first beetles appear, and then a mass extinction. The end Capitanian extinction affected 30 to 40% of both land and sea creatures. This was probably because of the volcanics of the Emetian traps in Sichuan, China. But that was just a taster, though, for the big one. The Permian extinction, 250 million years ago. That one wiped out 95% of all living species, known as the Great Dying. It's the worst such event so far. What caused it? Researchers in 2018 looked at geochemical data and established that it was likely to be an increase in greenhouse gas levels from, once again, massive volcanic activity, the Siberian traps. As well as CO2, this may also have released a large quantity of methane as superheated rock magma streamed through large areas of permafrost. This resulted in a rise of near-surface ocean temperatures by more than 10 degrees C, and ocean oxygen levels were depleted by almost 80%. That did for 96% of marine life, along with 70% of terrestrial vertebrates. It was the only mass extinction known to have affected the insects, 8 orders of which disappeared. Many others were vastly reduced in diversity, a reduction which in all the time since they have never fully recovered. But so long as that 4 or 5% of life survives, however humble it may be, then given a few million years to play with, life comes back to fill the vacant niches in yet another new form. Following the Permian extinction, we saw the rise of the first Arcosaurs, the forerunners to the dinosaurs. The Earth's climate became hotter and drier. Rainforests collapsed, and this was the invitation for the age of the reptiles, which evolved to exist in the drier land conditions. 230 million years ago, the first true dinosaurs appeared. For over 30 million years, they survived pretty well, but they were subservient to the Arcosaurs, which headed the food chain. 206 million years ago, we had the first true mammals appear, which were small nocturnal insectivores. In those days, it paid to keep your head down. The average temperature of the planet at this point was around 21 degrees C. The atmosphere was around 77% nitrogen, 22% oxygen, with 0.22% CO2, a lot more than the 0.04% there is today. The flora that thrived were ferns, cycads, ginkgos and the like, and coniferous plants were just beginning to appear. Then the vast interior of supercontinent Pangaea, which had been this hot, dry desert in its huge interior, it began to break up. As a result, desert began to be replaced by more humid environments. Dry environment plants gave way to lush forests, and the breakup triggered massive eruptions, which you're probably getting by now is rarely a cause for partying if you're a current life form. And sure enough, that triggered the Triassic/Jurassic extinction. And that extinction did for the Arcosaurs, but their loss was another's gain. The surviving dinosaurs quickly moved into the open ecological niche and became the dominant life forms on the planet. And they thrived for a very long time. I mean, the dinosaurs existed for 160 million years, and other stuff was coming online as well as we went. 128 million years ago, when temperatures started rising again after an initial brief cooling, the first flowering plants appeared. 95 million years ago, bees appeared. 85 million years ago, the first crocodiles joined the party. That makes it sound like one continuous progression. Of course, it's not really the case. There are advances and retreats, always based on the changing climate over that extraordinarily long time frame. And it's all going really well. And then comes a massive great asteroid. 65 million years ago, anything larger than a rodent was obliterated in either the impact itself or by the impact winter that followed. Something like 75% of all life perished, and the only dinosaurs that made it through were those that could fly. Those, of course, evolved into modern-day birds. As we know, each extinction is the opportunity for the next generation. So bye-bye dinosaurs, and hello to the age of mammals. Now, of course, every mass extinction is a tragedy. But you know, without that one, we wouldn't be here. There simply would not have been the vacant ecological niche for us to move into. So apologies to fans of the old movie 1 million years BC. No, humans and dinosaurs never coexisted. As we get closer to ourselves in time, so we get better evidence to give us a more granular picture of what happened climate-wise. Because so far this has all been broad brush global stuff. But as we know, there isn't a single global climate. It's always more complicated than that as it works out across the globe. We should expect that it's always been that way, at least since it was a big seething mass of molten stuff. So, for instance, oceans are major distributors of heat around the world. Now, the breakup of Pangaea and the moving around of the resulting continents made a big difference. Around 55 million years ago, there was the Paleocene-Eocene thermal maximum, when the world temperatures sharply peaked. And gradually from there, we saw cooling. Why did we see cooling? Well, one reason, not the only one, was that when the continent of Australia separated from Antarctica around 34 million years ago, there was significant general cooling as the Arctic circumpolar current brought cold water to the surface and cut Antarctica off from warmer waters. The Antarctica forests became subsumed by a major ice sheet, and sinking cold water began to flow northwards, which affected ocean temperatures across a wide area. 3 million years ago, we think. Some argue it could have been longer ago. There was another big change when North and South America joined together in the middle via the Isthmus of Panama. Suddenly, the newly joined landmasses were rerouting the world's major ocean currents to create the so-called Great Conveyor that is a huge factor in circulation and climate today. Resulting cooling temperatures and high precipitation produced an ice cap over the northern polar regions, 30 million years after the southern one had formed. It's worth noting, by the way, that while they'd been floating around independently for a few 100 million years, North and South American wildlife had been evolving separately. When they joined together, mostly the flora and the fauna of the south stayed pretty much where it was, but at least 29 North American genera moved south and proceeded to kick ass. Marsupial carnivores were the biggest losers. Make of all that what you will. Once we get to the last few million years, just a fraction of a moment really, compared to all those billions that we've been traversing, we're now used to a different version of ice ages. Rather than the planet-wide snowball Earth incidents lasting millions of years, we become used to the term Ice Age to describe recent periodic glaciations in the Northern Hemisphere, which started about 2.6 million years ago. These ice sheet expansions, glaciations, and contractions, interglacials, have been cyclic based on a number of influences that include variations in the planet's orbit around the Sun and the tilt and orientation of its axis of rotation. Warming periods seem to be kick-started by what's called the Milankovitch Cycle, as the Earth's orbit around the Sun reaches a position where it receives more energy. That initial warming leads to the release of more greenhouse gases, CO2 specifically, which then amplifies the warming further. And then conversely, when the Earth's solar orbit changes to give less energy input, by then significant amounts of that CO2 has been weathered out of the atmosphere, and then the process reverses, with the increase in albedo, the white reflective surface of the ice, providing the additional amplifier for the cooling to the glaciation state. So there you have it, an extremely broad brush history of the Earth, seen through the lens of the climate and through the lens of life itself. Here's my take. Firstly, it brings home to you what a miraculous existence we have as life on Earth, floating on this ball of rock in space. All the things that needed to fall into place to make us possible. And having arrived, you see that over geological timelines, life has been incredibly resilient. The Earth could turn into a massive ball of ice. Something would be hanging in there, ready to swarm back into action when the ice passed in a few million years. The Earth could turn into a hothouse, the ocean gets stripped of oxygen, lead to a massive die-off, and the next round of life forms would come back, remarkably different, but swarming into very familiar niches in that food chain. If we do get something catastrophically wrong in the decades or centuries or millennia to come, you can bet the same thing is going to happen again. I would give a huge amount to satisfy the curiosity of what that will look like. That's one aspect. Another aspect is that shorter term than geological timeframes, how precariously balanced each generation of life is. The environment has often changed in big ways with devastating consequences. When something changed on a slow timescale over geological timeframes, life adapted. Yeah, some species declined and others advanced, but it was fairly seamless. But when things changed quickly, and quickly could mean in this context tens of thousands of years, then you could end up with a mass extinction. In the modern day climate debate, people look at graphs like this one, a reconstruction of temperatures over the last 13,000 years, which of course is just a blink of an eye, and they make a big deal about whether the spike at the end has or hasn't gone above the peak of a more gentle wave in the middle. I've never understood that, and having gone through all of this for this video, I get it even less. The concerning thing is the steepness of the change, first and foremost. That is the remarkable standout thing about that graph. And the question to be asked soberly and without histrionics is, to what height can that spike climb before we kick into the wider consequences for life that we have seen in history? Now, I'm not convinced there are many that I trust to tell me the answer to that question. Firstly, because we really don't know. And I know enough to discount the people who preach complacency, to say that it's either not important or indeed, most bizarrely, it's not actually happening. And I know enough as well to discount people who say that we're already into the sixth mass extinction. The evidence for that is not at all present. The majority of the decline in the species that we've caused, it's more in population sizes than it is in actual extinctions, seems to be mostly about displacement, the loss of habitats. The mass extinctions were about the changing of a specific environmental variable that made life impossible for many species. Right now, we've not done those things. Certainly, if we were to carry on with that spike, merrily pushing more and more CO2 into the atmosphere without concern for the consequences, you would assume we will arrive at that point relatively soon, certainly on the geological time frame. At the same time, people have become so blinded by the recent period of time in the Goldilocks climate zone, it's entirely possible that they overestimate that fragility. If we come out of all of this with a hotter climate, more dry areas, different weather patterns to what we have today, some different extremes to endure, higher sea levels, that's a painful transition. Probably not the end of the world. The question is that threshold for life. You don't want to be playing chicken with that line just because you don't know where it is. It seems to me that you can look rationally at the history of the world, and in so doing you can confirm that preventative action taken carefully is justified. Not panic, not complacency, just a recognition of how respectful we should be towards the fragility of the environmental niche that we're living within. Now, we know very well, after all, how even small changes in the environment have affected the human race in our little bit of history over the ages. If you're interested in that story, I made a video you'll see over here, if you're watching this on YouTube, that goes through the Fascinating history of how people have struggled with, sometimes triumphed over, the climate. Why not give that one a look next?